Good day, everyone. Good morning for those of you in other time zones. My name is Kristofer Tingdahl, and it's a joy to present the OpendTect Volume Builder webinar. We'll quickly jump into this. We'll spend about 35 minutes in a presentation combined with a demonstration, and after that we'll open up for some questions. If you have questions along the way, you can always type them into the chat window of the GoToMeeting or GoToWebinar dialogues, and we'll either pick them up at the end of the session, or they will be answered by one of our panelists. Our outline today goes like this. We're going to talk about the volume builder, the basics of it and the principles. We're going to do some manipulations of volumes in OpendTect so you can see how things are done. We're going to emphasize on two applications of this, that is the Voxel connectivity filter and then the Horizon Cube guided interpolation. And finally, we'll open up for questions towards the end. So let's get started. And the background of the Volume Builder is that it was developed as a part of the velocity model building. My first demonstration will be manipulating velocity fields, not necessarily using the VMB plugin where you pick on semblances, but if you want to paint in velocities, if you want to manipulate volumes in an easy way, this is a tool that you can use. The difference between the Volume Builder and the attribute engine that we have in OpendTect is that the Volume Builder operates with all data in memory. In one way, it has less flexibility in how you can combine different things, but on the contrary, it allows much more flexible algorithms than in the attribute engine. As it is set up as such, it is also easier to utilize all CPUs on a processor. It requires more memory, though, because we have to load the entire volume into memory, and it's not fully adapted for multi-machine processing. On a single machine, it uses all CPUs it can find, but it's not easy to divide the calculations between multiple machines. The concept of the Volume Builder is that it allows a stepwise modification of volumes, and multiple steps forms a sequence, and each step modifies the output from the previous step. The whole idea of this came from my old professor who used to do this overhead slides, and what he would do is he put on a seismic section on an overhead transparency, and then on his he put on another sheet on top of it with maybe the horizons that were painted in, or maybe painted them in on the fly, and then on top of that he made yet another one with, say, with the geological symbols on top of it. So the idea is you have a number of steps or a number of layers that each add something to the image, and when they are made in sequence, they will together form an output. So in the example here with transparency, you have a green rectangle, a yellow circle, and a red triangle. When you put them together and stack them on top of each other, they will form the combined image. Each step is completely independent from the others in terms of dependencies, and that makes it very easy for third parties to add functionality. So if you want to have so if you're a software developer and wants a nice vehicle to easily put on new functionality on OpendTect, this is one of the places you might want to look. Each step in these in the sequence can be either calculation order independent or not, and that is a nice way to say, is the algorithm such that the output or the result will vary dependent on if you calculate one part of the volume first compared to another one? And the reason we need to keep track of this is that it's only when you have independent steps that you're able to calculate these on the fly. Today we'll mostly look on independent steps, but also a few dependent steps. So it really It depends on the algorithm what it's able to do or what it needs. And if you're able to evaluate these on the fly, or if you have to process the volume and then look at it. If we look in OpendTect, the volume builder is hidden by the arrow that is pointed out here by under the icon that is pointed out by the big red arrow. And if we press that, this dialog comes up, and this is the setup window for the volume builder. In the list to the left, you have all the different types of steps that can be utilized in the system currently. We're also adding steps to this, but this is what we have as of right now. And what you do is you move them over to the right list, and when you do that, you build up your sequence there. So let's go through some of the steps that we have right now in OpendTect. We have steps that are just painting tools. They just flood fill in values more or less intelligently. We have what's called the horizon-based painter that basically fills between two horizons. We have the body shape painter that takes a body in OpendTect and paints values inside or outside of that body. We have stored volumes that basically read in seismic data or attribute data from a volume on disk and just populates that and use that as a starting point maybe for further calculations. We have the surface limited filler. The reason that one is in green is that all the other ones are in the GPL version of OpendTect, while the surface limited filler is sitting in the VMB plugin. So unless you have the VMB, you don't have that. The surface limited filler is basically a more advanced version of the horizon-based painter. I will show you it in a short while. We have a number of gridding tools. We have the velocity gridder, and as it is white, you do not actually need to have the VMB plugin to use it. However, if you want to grid velocity picks, then you need the VMB. But you can, in the examples today, I will show how we grid sparsely sampled velocity volumes or ASCII functions or velocity functions that have been imported. We have the Horizon Cube Well Interpolator. Well, the Horizon Cube is one of our new products. It's a great tool. I'll show you it or introduce you to it a little bit later, but that is one thing that requires a plugin to run. It's not in the GPL version. Continuing, we have a number of filters. We have a smoother and a lateral smoother. The biggest difference between these is that the smoother itself is for rather small things, but it can also work in time or depth. The lateral smoother only works laterally, but is, on the contrary, made to, or it's very efficient making very large filters. Probably will, over the coming year, we'll integrate these two into one. And we have the Voxel connectivity filter, which we are quite excited about. I will demonstrate that in a short while. So let's get going into OpendTect itself and see what these tools look like in there. Just give me a second, and you should now see the main OpendTect window in front of you. It's the I'm using the F3 data set. If you've been around DG Sciences, we use that a lot because it's, and we also distribute it freely to anyone who wants it through our Open Seismic repository. I will just get started with showing up a seismic an inline through this area. The data itself is from the North Sea. We have at the top 1.8 seconds in this sequence, and I'm going to do some velocity manipulations in this area. So to get started with that, I'll go to the icon for the volume builder. I press that, and the first thing I will do is I will grid some velocities that I have. I have a sparse set of migration velocities that I've got from my processor, and I'm going to grid them so I can create a velocity volume from them. So I will use inverse gridding or inverse distance for the gridding. I could also use triangulation. And I will add velocity sources, and I will select my sparse vint model that I have, that I believe has every 50th inline and every 50th cross line in it. So it's quite sparse, but I have data throughout my survey. I press so I have to give that a name, so I call that gridded vint maybe. I press OK, and then you see it comes up as the first and the only step in this processing sequence. Now I'll just want to get my feet wet, so I will just process that. I will output a volume of that. I have to give it a name for the whole sequence, and I will process that. Write it here, a new velocity model, and I just do say from 400 milliseconds or from 300 milliseconds. So I just do a little bit of the range. When I press proceed, it will start up a new window where in the background it is now processing this this volume for myself. I will go back to OpenTect and we'll have a look at the output of that in a while. I can also shortcut this whole thing because this is a trace independent. Sorry, it's a calculation order independent step. So it doesn't matter really if I calculate one trace before another trace. And thus, I can right-click on my inline and add volume processing attribute. And there, I select the setup I just saved. I call it demo. It's the one what I saved it as. And it automatically on the fly calculates the gridding for this particular inline. It doesn't save it on disk or do anything about this. So this is what the output will look like for this particular inline. I can make it half transparent now, so we can see it how it lines up to the seismic data that is sitting below. So what I see here is that, well, it's not really lining up very nicely like in this area. It's not following the structure of the seismic data very well in this velocity model. So I will go about to see if I can change that and create a somewhat updated velocity model. Not really by picking velocities, but only trying to make something that is sensible from a geologic standpoint. So what I will do is I have a couple of horizons in this survey. This is one of them. I will use that to basically to start painting in velocities below this particular horizon. So I'll go into my volume processing tool. And I now have two choices. I can either use horizon-based painter, where I take this horizon and use it and paint it in between. I have a little bit more options in the surface limited filler. It's basically an advanced version of the body shape painter, but I do need to have the VMB plugin for that one. But I'll go with that anyway. And it opens up the setting window for the surface limited filler. The top of this dialog defines the geometry that should be filled. For instance, in this case, I will pick up the shallow horizon, the one I just displayed, and say I want to fill below this. I can either do above or below. If I have a lower boundary of my fill, for instance, I can go in and add a horizon further down and say I want it to be above. So you can put in as many limiting surfaces as you want to and say on which side that it should fill. And based on that, it's like an AND statement. It has to be below the shallow horizon, and it has to be above the lower horizon. Now, you can also do faults, but only if the faults are interpreted or represented in the system as horizons. If you want to have faults in natively, then you probably have to wait for another version. It's on our development list, but right now it's not the highest priority we have right now. For now, I will just remove the second horizon and just start filling below. Now, the filling of the velocities here follows the v naught plus k, so I will fill starting with a certain v naught and continue downward with a certain value. So I will say I will start from, say, 1800 meters per second. I will increase that with 1 meters per second per millisecond. Now, what's important when I have this equation is where is v naught defined? At what depth is it defined? Well, I'm here going to use the horizon because that is where I want to start. So I select the shallow horizon as the reference step for this. So then I put in velocity. Call this velocity gradient. I add it as a step. And then I can go in and basically reload the data. So it will basically do this on the fly for me. So let's now go in and have a look at this velocity. First of all, we see that, well, we didn't really hit a good mark here when it comes to this interface. We really see that there is a jump from the in the velocity at this horizon. So we didn't have the starting velocities right. The second thing I want you to see, and it's a bit hard when you have the data under, so I'll go ahead and I'll make the remove the transparency, so we only view the velocity that the model builder just created for you. If you see, I don't know if I hope you see it well, but you can see that there are stripes going down like here. You also see them down here, and they are simply caused by the fact, if we look at the horizon itself, we see that the horizon up here is actually a bit unstable. It's a bit wiggly. And basically, as we have a v naught plus a gradient going down, we are not well. Basically, that pattern will be progradated downwards in this setup, and that is not what we want. A solution for that is, and this is just using the general tools of OpendTect, is that I right-click on the horizon, I press algorithm and filter. So I'll just smooth its horizon, say with 21 by 21 filter. In OpendTect, that's defined as a step out of 10. Now save that as a new one, and I want to display it. So I have to give it a new name. And here I'm just smoothing this horizon because I need a better horizon as reference horizon in this setup. So I'm filtering it, and it will now save it and write it and eventually display it. So I should now be able to turn off the old one, and I should now have a new, much smoother horizon here. I also have a couple of other choices. If I want to do other types of smoothing, I could also try to snap it to the events. Then I would go through the seismic data and see if I can find a good event to snap to. But that should address these ripples that we saw here in the on the left side of it. Now the other problem we had was that we had quite a step in velocities along this one. So if we assume, let's just assume that the velocities we had initially before we started this horizon painter actually was pretty good. The one we outputted just when we did the gridding. We see now, if I go back to the processing, that the processing is now completed. So I will load that velocities onto my shallow horizon. So I right-click on it, select attribute, stored volumes, and there I select the new velocity model. I'm loading onto that horizon. And I will now display that. Well, first of all, you may think that, wait, this looks interesting. But if we actually look on the color table, we see that the values in this, it's very, very small differences in this. So it's just numerical errors that come there. Most of them sit between basically 1959 and 1960. So it is actually a good velocity that I could use as a V0 for this setup. I'll go ahead and I will save this attribute as a grid on top of the horizon that I've been working with. So it's now sitting as a grid on the shallow, smooth horizon. I'll now go into my volume builder, look at the settings for the velocity gradient, and I will do two changes in here. The first change is that I will not use a constant V0 for this horizon. Instead, I will go in and select the grid that I just saved, that I have extracted from the previous step on the volume builder. I will use the same gradient going downwards, but I will not use the rugged surface as my velocity or as my reference horizon. Instead, I will have the smooth horizon as that. Press OK, and I'll go to demo and I reload it. So let's have a look at what that looks like. We see that the gradient at the horizon, I'll turn it on and off. The step is gone, and the ripples that I had here on my left side, they're also gone, and that is because I'm now using the smooth surface as the reference surface. Now I will look at the other end of this area, and I will, for the time being, I will turn off the output from the volume builder, and I just want you to have a look here in this area. I have a shallow anomaly. It's probably gas pocket sitting in here that I will have a little look on. If I have gas sitting here, most probably I have slightly lower velocities in this area. So we'll see on some tools how I can put in those velocities into my volume builder output. I have, for the purpose of this, I've tried to characterize these anomalies in some way. And what I've done is I created a very smooth, I have to put on some transparency on this one, a smooth energy. So I calculate the energy from the seismic data, and then I run a smoother on it to just get a blurred image of where this is. Then I loaded that into the volume builder, and I there created an isosurface. And from that isosurface, I created this body that you see if I can turn off the energy. So I have here, I've created this body. It's a 3D body that I've stored on my system. It's created in the volume viewer by taking an isosurface through the energy volume that you just saw. I'm going to use that and put in a slightly lower velocity in this area based on the on this particular body. So again, I open my volume processing and I go in and use yet another painting tool, and that painting tool is available in the free version of OpenTect. That is the body shape painter. I press this arrow to get it into my list, and I say the energy. I specify the body that I want to use to paint with, and I want to say, well, I should have looked in the velocity field what velocities I have there. They are just sitting at 2,000 meters per second there. So let's say I will just put in, say, 1,900 meters per second inside this body, and outside it will be transparent. And with transparent, I simply mean that it will keep the value from the previous step in the volume processing. So I will call this shallow anomaly. Okay, I press OK, and I just go in here and I say reload. So now it's doing the gridding, and then it's going ahead and doing all the steps in sequence as I have defined. I'll turn off the body, and you see that I just bluntly I've painted in values into this field based on this body. And you can do that with any body you have defined in OpenTect. You can either paint inside or outside, or both. Now, I do not like the sharp edges that I just created around this, so I will end this little exercise by putting in a smoother here. So I'll go on and smooth it and make a box filter, give it some size, and just call it smoother. Okay, and the last thing I'll show in this demonstration is just the output of that. So using existing volumes, existing horizons, and existing bodies, I've been able to create an updated velocity model. And there's really no limit in what you can do in this type of setup. If you add things, you manipulate things, and add them one step at a time. Every step is quite simple, but in the combination of them actually becomes quite advanced. So now it's probably filtering here. So I'm hoping that it's finished soon. Just hold on. There we are, and we have the smoothed output from this exercise. So this is the updated velocity model that I did using quite some simple tools, but still in combination quite powerful. So now we'll go back to the Voxel connectivity filter, and that is a tool that we just developed. It's released in version 4.420D, which is the patch we just released in October. It is a development that was sponsored by Tingdahl Technologies. Tingdahl Technology is a processing company in Calgary. They have a unique product where they work with the duplex wave migration. That is, they model waves that bounce on faults as well as at the normal reflectors, and use that to map out faults. And they needed this filter, a similar filter, but we're very thankful for them sponsoring this development. And we're also very grateful that we're allowed to release this in the open part of OpenTect to the benefit of the entire geological and geophysical community. This is a calculation order dependent filter, which means that in none of the examples that I'm going to show, it really matters which order I calculate something. So I have to run the whole volume, and I cannot do it on the fly. So, but we'll look into that into a minute or two. Let's go to some theory. And the example I've chosen is a curvature attribute. It is from the same survey that I just looked on. It's a little bit further down, and it basically, the curvature attribute maps a large number of small-scale fracture zones in the subsurface. And a little bit depending on what you're doing, you may be are interested in going into the fractures. If you're dealing with unconventional place, you may be interested in going into the fracture zones, or if you think there is a water break, you actually want to stay clear of them. So. But it's very interesting to know, is a certain fracture connected to another one? So if we look at the two ones we have here, is this one connected to that one? Well, maybe not on this level. We can play with the color table, but then it's hard to tell. And of course we can look at the time lines above, the time lines below, and the end line to the left and end line to the right, and cross line up and down. But it's quite tedious to actually see in 3D what is connected to what, and that is what the Voxel connectivity filter is aiming at. I see the same setup in a 3D perspective. So the question is, are these things connected? And are they connected to the neighbor ones and the other ones? What is connected to what? And the voxel connectivity filter does this in a couple of different steps. The first step is that it's applying a threshold, and that threshold is user-defined. It's something you as a user has to put into this. The second thing is that it groups the data. So each voxels over the threshold that are connected to neighbors that are also over the threshold. And each group of connected voxels, they form a body together. And then once that is done, all bodies are sorted on their respective size. So the output of that is basically it groups together, in this case we color identical things that belong together. And the third step that is optional is that you may filter on the size. If you're not interested in small bodies but only big ones, you may say, well, I want to filter out the smaller ones. So you can put on a minimum criterion on that. Step 4 is to define the output from the voxel connectivity filter. And first of all, we have to define what should be inside the bodies. It could be the body size. We can put a unique identifier on them. We can put on a specific value or make them transparent, that is, they have what the input was from the previous step in the volume processing. Also, we have to define what the value should be outside the bodies. It can either be undefined or we can set it to a specific value. So let's quickly jump into a demonstration of this. Just give me a second. Just give me a second. So I am now inside OpendTect again. It's the same survey I was in previously, and basically the area that you see down here is the one that I pointed out in the PowerPoint before. So are these connected or not? Well, to get started with that, the first thing we do is we have a look at the value spectrum of what we're currently displaying. So let's go in and look on this particular line. We'll just have a look at the histogram. And basically what we see is that the red ridges on this display are low values. So we see that on the color table. And if we're looking for the extreme ones, say we can look maybe somewhere at minus 0.002, maybe that would be a nice place to put a threshold. So I will remember that, and I'll go into my volume builder. The first thing I have to do, apart from getting rid of all the old stuff that I had in there, is that I need to load the volume in that we're going to run this operation in, and that's the stored volume. So basically with the data I'm seeing here, I've calculated that in a volume, and it's called most negative curvature, and I give that a name. Most neg. Okay, so now we read in and populate a volume in memory with the volume that we have on disk. The second step in this is that we want to apply the voxel connectivity filter. I press the arrow there and I get the user interface for it. Well, first of all, I have to define my threshold. So that is, I said, minus 0.002 is the one I will play with. Then we have the connectivity that basically tells you how the voxels may be connected to each other. I will use 6 neighbors. You can read in the manual what you want to do. The third step is optional. That is how many, what's a minimum size of the bodies you want to allow. And I want everything in here, so I'll just keep that at 1. And the body output, I want to basically I wanted to number the bodies, and it will do that in racking them. So it will basically call the biggest body, it will call that number 0. The second bigger, it will be number 1 and 2 and 3 and 4 and so forth until the smallest body. The rejected output I could do undefined, but well, since the biggest body will be 1, I will just go into negative slightly. So I call this my voxel connectivity filter for the curvature. Okay, that is defined. As this is a computation order dependent filter, I have to process my whole volume to get this going. So I will at least process the area that I'm looking at here. I press OK, and I will run not the entire survey, but the area that I'm currently in. And I will call this voxel connectivity curvature. I press OK, and I will get, it will calculate this in the background, but fortunately it's pretty quickly. So now it's reading in the old volume. Now I'm running the voxel connectivity filter, and now it's writing out the results to disk. So I'm waiting for that. It is a bit slower than I anticipated, so but we should be there in just a few seconds. So now we're finished, and I can go into OpendTect again. On this time slice, I will add an attribute, and there I will display the voxel connectivity curvature, the one I just calculated in the background. So this is what it looks like. Well, first of all, you see we have kind of funny red edges on this thing, and that is simply because we're dealing with integer classifications, and OpendTect normally expects there to be floating data. So there's a small trick you can do, that is right-click on the time slice or inline or whatever you're at. You go into Properties, Texture, and say this is a classification. This is what I want. Press OK. So now it doesn't interpolate, but you see the individual voxels that they actually are in the seismic data, or on disk. Now the second thing is that you see, if you look on our color table, that the values here represents which body each thing belongs to. So everything that is purple is -1, which means it doesn't belong to a value. Then if we find a 0 somewhere, that means we're at a certain, see if we have a 0 somewhere. I cannot see one right now. But they are now number up to, say, body 900. So we'll just look at, say, the 150 biggest bodies, and then we get a more sensible color table to look at. So if you remember what we were interested on, well, now as we have turned off the interpolation, we get a somewhat crappy image here on the curvature attribute. But if you look on the body we were interested on, which is this one right here, I'll turn off the VCF curvature, and I'll look down in the status bar. I see that as number 118. And I'll walk over to the other one that is also number 118. So they are actually, although not on this particular slice, they are somewhere connected. I will use that. I will go into my, I will map out just this particular body. I'll look in my attribute calculation window, and I will define a single body. So I will basically use a mathematics attribute and say if the body ID equals to a certain constant, which is defined as 118, then I will output a 1, otherwise I will output a nil. So I can then go in creating, opening a little volume render box. I'll go out here, and we'll now be able to slide through. Something is, see where my actual body is. There it is. I will turn off the inline and the cross line in this view. And basically see the blue dot coming up here. That is actually body number 118 going through the data. So basically I have in this volume, in this attribute, I have value 0 everywhere, but where I have this particular body, I have number 1. So I can go into the volume render or volume viewer and say I want to do an isosurface of this thing. And since I know my value is 1, I'll just create an isosurface based on that. So now I'm creating a body or an isosurface that I later will convert to body based on this particular fracture zone that I have, that I've isolated through my voxel connectivity filter in OpendTect. Should be finished in a second. I press OK. And I can then turn off the Z-slice. And here, ladies and gentlemen, is that particular fracture zone, and we can see that indeed the body is connected a little bit above the time slice that we were viewing. That is the connection that we didn't see on the particular time slice we were at. If I want to, I can then right-click on the isosurface. I converted that into body, and I can save that as body in its own right. That if I wish to, I could again use in the volume builder. So I just give that. That is fracture 118. Save that. Okay. So if I later pull up OpendTect, I'll just have saved that body. So that concludes the voxel connectivity demonstration, and I'll go into the last demonstration that I have, and that should be fairly quick. So I go back into PowerPoint, and we'll have a quick look at the horizon cube interpolation application in the volume builder. Now, some of you are very familiar with the horizon cube, and some are not. I will just briefly explain that the horizon cube is a very dense set of correlated 3D stratigraphic surfaces. They are created automatically from the seismic data by one, we map out the framework horizons, say the top and the bottom of the sequences. We map the faults if they are large. And then we use the dip and azimuth derived from the seismic data to create all these internal surfaces in the subsurface. So again, we start with seismic data. We create the dip and azimuth. And once we have the horizon cube, which is a complete map of the subsurface structure, we can do a number of things. We have applications for vertical correlation, for sequence stratigraphy, but we're going to look a little bit at the geomodel application of this. And the whole background of that is simply that we have the rock properties, whatever they may be the porosity or acoustic impedance or whatever it may be, they're defined at the wells. But if you go to a reservoir simulation, they're not interested in wells. They want to know in a volume mode, what is the porosity, what is the different rock properties, so they can push that into their models and make their simulations. Now, the problem is, of course, how should the volume be populated? In OpendTect, we have a number of different approaches to this. One of them is with neural network. We may go through inversions or a combination of these. But I want to point out that the horizon cube has mapped out the complete structure of the geology in the reservoir. And if we're going to do an interpolation of the rock properties, we should be much better in using that structure when we do the interpolation. And that is what we do. So I will quickly go back into OpendTect. We'll close down what we looked at just a minute before, at our nice fractures. And let's just go here. So here we have the middle line of the survey. Just put on a grayscale simply because my colors are nicer than I want to put them on. I have already calculated a horizon cube for this area, and what you see here if I zoom in is that you will see that the horizon cube is all these stratigraphic surfaces. They're correlated, they're never crossing each other, and they're sitting there mapping out the complete structure of the seismic data on seismic resolution. So I have the slider here just to see how it could work. I can slide through the buildup of my sedimentary environment, and thus I'm actually sliding through geologic history. I can easily isolate areas of certain facies or certain system tracts with this tool. But that is not the main application of what we're doing today. We will use this tool to interpolate the well logs from the 4 wells we have in this particular area. So we have 4 wells in the area. And I will see the 4th one is there, yeah. And they all have porosity logs. But as the problem is, if I want a porosity volume out of this, how do I get that? Well, that is where we have a new tool in the Volume Builder. And this, to use this tool, you do actually need to have the Horizon Cube plug-in to OpendTect. But since it's so powerful, I will show it to you anyway. So I press on Horizon Cube Well Interpolator. And what we will do is simply we will go from these well, follow the structure of the seismic data as mapped out by the Horizon Cube, and we'll use that, and following that path, we will do the interpolation in a geological sensible way. So I select the Horizon Cube I want to use. I don't want to do anything above or below this where the Horizon Cube is defined, and I have to tell the system what wells to do. Well, in this case, I'm interested in the porosity, and the porosity is available on on all the 4 wells. So I call this the Horizon Cube porosity. Press OK, and then I press OK. This is a computation order independent tool, so I can actually calculate this on the fly. Now, it actually does take probably a minute to calculate, so and I'm running out of time. I actually pre-cooked this, but this is essentially what the output from this process would look like. So what you see is that I have a porosity. If I move over, I see it's ranging between around 29 and 30%. I have a porosity, and it's interpolated in a geological sensible way, following the structure of the data. We can see, for instance, if we zoom in here, it's kind of hard to get a good view here. You see this layer here is then represented in here, and so forth, and interpolated throughout the volume of the seismic data. And then I'll just finish in a second. And so to summarize what we have learned today, we have looked at the Volume Builder, and it's a new free tool in OpendTect. And each step in it is quite simple, but together all these modules can do quite powerful things. And I think that is something that will aid you in your interpretation work. So that leads me to only one remaining thing, and that is I want to thank you for your attention, and I will open up for any questions.
Well, thank you, Kristofer. This has been a very nice webinar, and we've had several questions coming through as we've been talking here. So I'm going to forward a few questions over to you. Let's see. Here we go. We have one question actually regarding the very first example that you gave earlier. Are you there, Kristofer?
Yes, I'm here.
Okay. Yeah. So I'm forwarding a few questions over to you regarding the very first example with the Horizon cube, or with the Horizon painter in the Volume Builder. So if you could take a quick look at those, and for the other attendees out there, if you would like to ask your questions, then you have two options. You can raise your hand, and in the order that you have raised your hand, I will unmute you so that you can ask your question directly to Kristofer. Also, if you would like to remain anonymous, you may type in your question and we can read it aloud and forward it to Kristofer. So please send your questions.
The first question I have here is, I think it's regarding to the example where I painted velocity with using a horizon, and the question is, what does it do at the horizon, above or below, or has the equal? Well, I would have to go in and look in the code. I do think that if it's, well, since it's V0 plus K, well, we simply calculate the distance from the center of the sample to the horizon, and based on that, we throw that distance into the V0 plus K. So if it's equal, then it will actually paint in the V0 value. Now the question is, what happens, that is on the lower part of the dialog. The upper part of the dialog, where you define the geometry, I do think that it's, well, I simply would have to go in and look into the code there, if what it does, if it's exactly equal there. So I do not have the answer right away for that question. If that remains a question, then please come back to us afterwards. Let's see, then I have the question from another user, and what is the size of these fractures? I would simply have to go in and look in OpendTect. One moment. I have to pull up the Z slides and go to them. Basically, as I know, here's the fracture we were looking into. We have a measurement tool here. We can go in here and do a measure of this fracture. At least I thought so. Maybe I'm doing something wrong here. That's the problem if you send the CEO to do the actual driving of these things. But each voxel here is 25 meters, so you could probably say that from the top to the bottom, say there we have 10 and there were 20, so 20 times 500, 20 times 25 meters would be 500 meters in this case. Go to the next question. And if you still have a question, you just re-ask that.
Well, we do actually have another question in here that's a little more of a curiosity question. They were wondering about the texture classification, where you changed these the voxels to showing up in one color as a classification rather than interpolating. And they're just wondering when that function was added into OpenTect.
That was added. I remember it very well. It was, I had a client in the office telling, why can't you do that? And that was, I think, in April this year. So I think in any version of OpenTect 4.2 it's in, because I changed it the same afternoon as they had left, because I thought, well, it's dumb that we don't have it. But yeah, it was added then, and you can only do it, you cannot do it on individual layers on the displays, but you can only do it for all the layers. So you can go on this particular time slice and then go in and properties, and then texture, and then interpolation or not. So the answer is probably OpenTect 4.2.
All right, well, I don't have any more questions coming in at this time, so if you do have questions, please type them in or please raise your hand. I am getting several thank yous coming through, so great job, thanks, great review. So if you do have any questions, please type them in or raise your hand. I'll give you another minute. But in that time, I want to go ahead and thank our presenter, Kristofer Tingdahl, and thank our attendees for participating. Also, I would like to go ahead and make the announcement for the next webinar next month, where Arnaud Hoek will be presenting the VMB, the Velocity Model Builder. This is something people have been asking about a lot. It's becoming a lot more popular, and people are wanting to know the workflows. So please join us next month for that webinar. The invitation for that will be sent out along with the link for the recording of this one, which will be available at the end of the week. So please be checking your emails for that. We do actually have another question that's come through. Kristofer, the question is, what happens if there's not enough memory for the entire volume?
If the program has done its job, it will post an error message, and it will say too little memory. If the program has not done its job, which is probably me because I've done the majority of this, it will crash.
Well, that's a very clear answer. Okay, well, thank you, everybody. If you do have any more questions and you didn't get them in during the webinar, please feel free to email us at webinar@dgbes.com. So thank you, everybody, and we'll see you next month.